In the last video, we studied something called the washer method, but we really didn't get a chance to do any examples of the washer method. So that's what I want to do in this video. We want to take a look at a solid of revolution that has a hole in the middle. That's why we're going to need the washer method instead of the disk method. And we're going to try to find this guy's volume. So here we go. The region that we're going to be revolving is the area between the function x squared and x cubed is bounded between those two curves just in the first quadrant, and we're going to revolve this area around the x-axis to create our solid. Okay, so the first thing we need to do is graph x squared and x cubed and figure out what this bounded region looks like in the first quadrant. So to speed things up a little bit, I went ahead and graphed both of these already. So here's x squared and here's x cubed. And so I see it. Here it is. There's this region here. But I've got some questions now. I need to know, for instance, how far out does this go before they intersect? That's going to be important for the problem later on. And I know that one of these is x squared and one is x cubed. But just at first glance, because they somewhat look similar in this region, I need to know which is this curve and which is that curve. That's going to be important in just a minute as well. So let me hide these layers here real quick. All right, so here what I've done is I went ahead and drew just this region. I got rid of all the extra stuff that we didn't need, and I drew its reflection below the x-axis, kind of hinting at what this solid of revolution would look like if you revolved it around the x-axis. So if you spun it this way around the x-axis, you would get a solid that looks something like this. And so first of all, you have to do this from time to time. You might have to figure out where these intersection points are. So if you want to do something like that, it's pretty simple. All you do is you would take x squared and you would set it equal to x cubed. And so if this was other functions, you would just set them equal to each other, because that's what happens at an intersection point. The functions are the same. And so, we could, let's say subtract x squared to the right-hand side, x cubed minus x squared. We have a common factor of x squared we can pull out, and we'd have x minus 1. And so this leads to either x being 0 or x being 1. And so sure enough, I see exactly where these two places are. I've got, let's see, x equals 0 right here, and x equals 1 right here. So those will be important in just a minute. Now, another thing that's also important as well is I need to know for the washer method which is this outer curve and which is this inner curve. And so this is a little bit counterintuitive. Sometimes students will struggle with this. X cubed seems like it would be bigger than x squared, and oftentimes it is. 5 cubed is bigger than 5 squared. However, between 0 and 1, if you have a small fraction or a small decimal, squaring it actually turns out to be bigger than if you cubed it. So in fact, the outer curve here is x squared, and the inside curve here is x cubed. So that's important to notice. All right, so now from here we're going to need to bring out our washer method, because I think we're about ready to start plugging things in. So here's your washer method. It was pi times the integral from a to b. This will, in our case, will be 0 to 1. So I'll jot that down in a minute. Of the outer curve squared minus the inner curve squared. Now, if you didn't have this part to it, this would just be the plain Jane disk method, because there's no inside to be subtracting. But because we have a piece missing on the inside, a hole in the middle, you have to subtract out the volume of this inside piece right here. So we take the outer radius squared, so that's x squared squared minus x cubed squared. Compute this algebra and we're done. So let's see how we do with this. All right, so we will take the volume to be pi times the integral from 0 to 1 of x to the 4th minus x to the 6th. When you have a power to a power, you multiply, dx. So I'll tell you what, let me take some of this away right here so I have some room to work. Delete this real quick, okay? And then, so now I've got some space to actually write some stuff down. Okay, so I'll take this integral, I'll move it up here so I can keep working. All right, so the volume would be pi. Let's go ahead and integrate now. We'd have integral of x to the fourth would be x to the fifth over 5, power rule, minus x to the seventh over 7, again power rule, bracket 0 to 1. That's a fundamental theorem of calculus. It says if you want to do a definite integral, you take its antiderivative, you plug in the upper limit, you plug in the lower limit, and you subtract. Now the nice thing is when you plug in 0, we'll get 0. So all we really have to do is plug in 1. So I'll really have 1/5 minus 1/7. 1/5 minus 1/7. And so if my algebra is right, I think that would wind up being 2 pi over 35. And I did skip a couple steps there, but you can check my algebra on that just on your paper. But just to speed things along, I believe that's what the volume would be. So this is going to be the volume of the solid of revolution with a hole inside. And again, the reason we needed a washer as opposed to just your plain Jane disk method is if you look at one of these representative disk here, you'll notice right off the bat that it's got a hole in it, which means you're going to have to take the outer radius squared minus the inner radius squared for your integrand. So you've got this extra term tacked in for the washer method. Sorry, I erased that when I erased some of that earlier stuff. For the washer method as opposed to the disk method. So anyways, hope that helps. If you want to find some more videos on the disk method or the theory video on the washer method, visit my website, fireflylectures.com.